Raspberry Pi Pico is a powerful microcontroller from the Raspberry Pi Foundation. NEMA 17 stepper motor is widely used in robotics and 3D printing projects. Unlike the usual direct current motors, it moves in small steps depending on the signals given to it. Hence, it is possible to know its position without an additional sensor. A driver unit like A4988 is needed to drive the NEMA 17 stepper motor with a microcontroller. A more powerful driver is the DRV8825 driver, which I have not purchased yet. A4988 driver has features like adjustable current limiting, protection against overcurrent and overtemperature, and the facility to choose among 5 microstep resolutions. It can operate with a wide range of supply voltages from 8 volts to 35 volts. About 1 ampere current can be delivered without a heatsink or forced airflow cooling. With heatsink and good cooling, A4988 driver can take up to 2 ampere current per coil. The driver supports full, half, quarter, eighth and 16th step modes of operation. Though there is a thermal shutdown circuitry, there is no reverse voltage protection for A4988 driver. A4988 has been photographed with the heatsink so that the processor is not visible. Here is a photograph taken before the heatsink was fixed. Image has been inverted so that the processor name can be read. The preset potentiometer is seen at the top in the second image, while it is at the bottom in the first image. Both these are magnified images. V-mod pin at the top can be used to supply power for the stepper motor, which may range from 8 volts to 35 volts. Pin adjacent to that is a ground pin. Lowermost pins on the same side are the VDD, which drives the internal logic circuitry running on 3 to 5 volt. There is a ground pin near that as well. MS1, MS2 and MS3 pins on the opposite side are the micro step select pins. If all the three are set at low or 0 voltage, the stepper motor works in full step mode. If all of them are set at high, then the stepper motor functions in the 16th step mode. Other permutations and combinations permit use in the other step modes of the stepper motor. Below that, there are step and direction pins. Step controls the micro steps of the motor, while direction controls the spinning direction of the motor. Remaining pins on that side are the enable, reset and sleep pins. Low input to the enable pin enables the driver. Low input to the sleep pin puts the driver in sleep mode with minimal power consumption. Low input to the reset pin causes it to ignore step inputs. It can also reset the internal translator to the initial stage of the motor. Remaining pins on the other side are the 4 output pins 2B, 2A, 1B and 1A. They can be connected to any bipolar stepper motor with voltages between 8 volts to 35 volts. The number 17 in the name of NEMA 17 stepper motor refers to the dimensions of the faceplate, measuring 1.7 inches on each side. This motor moves in steps of 1.8 degrees with 200 steps for a full revolution. NEMA stands for National Electrical Manufacturers Association, which brought out the specifications for stepper motors. Larger stepper motors will have larger number. Though there are 6 leads coming out of the NEMA 17 stepper motor from 2 coils, 2 of them are center taps, and I have not connected them here. Other than checking continuity, integrity of the coils can be checked by connecting an LED across them and rotating the shaft manually, which causes the LED to light up. This particular motor has a gear fitted on the shaft. I use the circuit diagram given at howtoelectronics.com. First, the 2B, 2A, 1B and 1A pins of the A4988 driver were connected to the 4 wires from the stepper motor. They are the pins for driving the 2 coils in the stepper motor. 100 microfarad decoupling capacitor was then connected across the stepper motor power supply. That was across the V-mode and ground pins of the A4988 driver. Next, those 2 pins were connected to a 12-volt battery using a couple of jumper wires. G16 pin of Raspberry Pi Pico was connected to direction pin of the driver and GP17 pin to step pin of the driver unit. They are the pins for controlling the direction of stepper motor rotation and the step. 20 microfarad decoupling capacitor was connected across VDD and ground of the driver unit. That is the connection for the 5-volt power for internal logic circuitry. These were in turn connected to the V-bus and ground pins of Raspberry Pi Pico. The 5-volt power was obtained by using a 7805 voltage regulator IC, which would step down the 12-volt battery power supply. MicroPython code for basic stepper motor control was obtained from the howtoelectronics.com page and pasted into a Thorny window, just as I had done for the previous blinking example LED code. Then I clicked on Run Current Script in the Run menu of Thorny, and the stepper motor started moving in tiny steps. This is the first step in my future project of getting an antenna rotate according to computer code. I know it is a long way off, but I do dream of getting my Moxon Yagi for satellite operations controlled by a stepper motor and G-Predict software in the long run.